Hey everyone in Chemistry 40 land, this is Dr. Carroll here. We are now looking at Unit 1, which is Atomic Theory. Lecture 2. I guess I need to choose a pen. Here we go. Oh, nice. There you go. Unit 1, Lecture 2. It's all about spectroscopy today and transitions to see lines. Now that we have looked at electromagnetic radiation, part of the wave-particle duality, we are going to see the photons reacting with electrons and other electromagnetic energy causing emission spectra. So spectroscopy this is in our booklet here, and continuing from our last lecture, spectroscopy is the interaction with electromagnetic radiation with light. And one thing that'll be helpful in probing what a atom is looking at an emission spectrum, and it's unique for each element. It's like a fingerprint. I'm going to write the word there, fingerprint, for every element. So and I will communicate to you a video for you to watch. I won't put the video within here, but in our daily lesson plans, I'll tell you a video to watch that shows how a gas discharge tube, so it's a glass tube containing just a little bit of a gas, can be excited by having a voltage placed across it, and then those atoms can de-excite and go through a prism, and only certain lines are seen in the visible spectrum. There's other lines in the non-visible spectra, but we don't see those with the eye, or in a photographic film. But the visible spectrum, only certain are seen, and this confounded the scientist 150 years ago who thought that the spectra should be continuous, but it wasn't. There were only certain lines, which made scientists say, okay, energy can't be continuous, it has to be discrete, it has to be quantized. You think of quantized, you think of discrete. So this was a real revolution, but that's what the data showed, so that's what we have to deal with. So photons are emitted when a atom in an excited state de-excites, and each atom has its own distinct pattern because the energies are different. Every atom, different elements, has different number of protons. So the photons represent the energy differences between what are called energy levels. And in an emission spectrum, we're looking at energy released. There's another kind of spectrum called an absorption spectrum where energy is absorbed, and the electrons go to a higher energy level, but more common studies are done of emission spectrum. They're easier to interpret than absorption spectrum. Okay, so again, a black body spectra would be all the radiation, but we see here, as I'm looking at some pictures, and again, I'll direct you to some photos, or you can just Google the photos of line spectra for common elements like lithium, sodium, potassium, rubidium, cesium, mercury, neon, as I see here. And there's different patterns of lines, different colors, different intensities. This, by the way, is why when you have fireworks, when you're getting the intense heat, you get different colors depending what your ingredients of your firework are. Right, like sodium will give you beautiful yellows, and coppers will give you blues, and you can put in greens and strontiums. You can have all these mixes, and you probably know that right down the street from where our school is, we have a world champion Archangel firework company, which wins all these international tournaments. So they definitely have to know everything about emission spectra, flame tests, things like that. So I just said the thing about the fingerprints and the fireworks. So let's go to page 6. So we're going to absorb energy, and then we're going to de-excite, because atoms don't like to stay very long in an excited state. They want to go back down to a lower energy level. The lowest energy level possible, by the way, is called the ground state. The ground energy state is represented by the letter N, which is the energy level number. It's also the principal quantum number. We don't really talk about quantum numbers in this course, but next course definitely you will. And when the electron falls down to a lower energy level, it emits a wave with a wavelength that corresponds to a color of visible light. Okay, so you have many spectral lines that are observed. Hydrogen, there's 4. This, because this isn't a color diagram, you only see 1. Look on the net, type in hydrogen line spectra, you'll see 4. Third energy level down to the first energy level. That's not true. It's actually down to the second. That should say second. Up to the second energy level, red color is omitted. And if it's coming from a higher, like from the 6th down to the 2nd level, then it's violet, right? If it's a larger jump down, then you'll have a higher energy photon released. Higher energy means if it's in the visible spectrum, it's going to be towards the blue end as opposed to towards the red end. And these are all called electron transitions. And so here I have an example of the ground state in various excited states, and then they fall back down on page 6. Page 7 is upside down. So I gotta rotate that. So this is gonna be fun. Always a good time. Let's see, I think this is my rotate button. Rotate, rotate. And somehow I'm on page 15, which I probably didn't want to be on. So let's go up here. And that was fun. You got to know this backwards and forwards, eh? There we go. Okay, so here on page 7, I have a energy level diagram for a hydrogen atom. Why hydrogen atom? Because it's the simplest one. You got to start somewhere. So let's start with hydrogen atom, where we have 1 proton and 1 electron. I don't care about the neutrons here. I'll assume there's none, but it doesn't really matter because neutrons don't have a charge. So you don't have this electrostatic force of attraction between positive and negative species. So the ground state is the most negative in our definition, and I'm going to use units of kilocalories per mole. Kilocalories per mole is a unit that is sometimes used. You could have joules per atom. There's various ones, but kcals per mole is nice because the numbers are pretty comfortable for us. So thousands of calories, that's energy per mole. A mole, remember, is 6.02 by 10 to the 23 atoms. So in the ground state, we have n equals 1. That is our most stable situation. It's called the ground state. The electron, which I represent by this half arrow, is sitting most of the time pretty in its ground state. Now if we zap it with energy, we kick it up to the first excited state, which is the 2nd level. These things, Lyman, Balmer, Paschen, Brackett, Fun series, let's not worry about them right now. So the first excited state, there's a certain energy associated with that, minus 78.4. In the ground state, minus 313.6. If instead I kick the electron up from the 1st level to the 3rd, the energy would be in the 2nd excited state, minus 34.8 kcals per mole. In the 4th energy level, it's minus 19.6. 5th is minus 12.5. If you go up to the infinitely high energy level, well then the electron's gone from the hydrogen atom, so it's 0. It's now called a free electron. Notice in this energy level diagram that the spacing is not the same. Some books, the older books, say, oh well, the energy level diagram for a hydrogen atom is like the rungs on a ladder. And well, that's not true because rungs are evenly spaced until you get to the top of the ladder. But another one said it's like an adjustable bookshelf. I like that analogy better because you can adjust the spacing, the vertical spacing between the horizontal slats in a bookshelf more easily, and you can have the distances decrease as you go up. So then you're going to have just like really teeny tiny books at the top of the shelf, right? So if you're in the first level and you zap with X-ray, whatever, to get it out to the infinitely high level, then you have ionized the atom. And so the amount of energy would be called the ionization energy to go from the first level to the infinitely high level. The formula to calculate for a hydrogen atom how much energy is in a given level is given by the equation minus 313.6 over n squared kilocalories per mole. Okay, so if you just plug those in, you'll get those numbers, as we said there. If it was n, not n squared, well, yeah, then it would be equal spacing, but it's n squared, so the spacing gets more and more close together. The energy released when an electron falls from a higher to a lower level is called the transition energy, n initial to n final. So the transition energy, delta E, n initial to n final, is E n final minus E n initial. So minus 313.6 over n final squared minus 313.6 over n initial squared. And we can just factor out the minus 313.6. So it's minus 313.6 times, in brackets, 1 over n final squared minus 1 over n initial squared. So from 6th level to the 2nd level, here's an example. It's be minus 313.6 times 1 over 4 minus 1 over 36, and we get a value for that. And we're just going to hold on for 1 second. And I'm back. So I just was able, that was just a chance for you just to think about and stare at this equation. So you work it out and you get minus 69.7 kcals per mole. If we went from the 3rd to the 2nd level, it'd be minus 313.6 times 1 over 2 squared minus 1 over 3 squared, which is minus 43.6 kcals per mole. The negative sign means that energy was released. If I went from 2 to 3, well, then it would be positive 43.6 kcals per mole. So I'd have to increase, I wouldn't have to, I would pour in energy to have the electron move from the 2nd to the 3rd level. Okay. Now let's flip it around again. So here's example 3 on page 8. Energy released when you go from the 7th level down to the 3rd excited state. Now be careful here. Some people will do from the 7th level down to the 3rd level, but that's not right. The 3rd excited state means the 4th level, so n equals 4. So it'll be minus 313.6 times 1 over 4 squared minus 1 over 7 squared. So you get minus 13.2 kcals per mole. And from 1 to infinity, well, then you put in 313.6. Okay, so that's transitions, and that's good for the second. Short, but there it is. Next one, we'll talk about atomic orbitals.